Hello and welcome. This is for intermediate macroeconomics. In this question, we're given a production function, this guy right here, and we're given some values for K, capital, technically land in this question, but it's basically capital, and we're given a value for L, labor, and then we're going to take that production function and find out total output. We're going to find out the real wage rate, the rental price of land, and then we're going to find out the share of output that goes to labor. After that, given a shock to the economy, we're going to kill half of the population, half this labor component, and see the effect of that on output, wages, rental price of land, and the share of total income that goes to both labor and capital. If you want to skip ahead to any of these parts, have a look at the video description, and I'll have a link to the timestamp, so you could skip straight ahead to solving a particular problem. With this is like a nitty-gritty, grinded out kind of problem where we're plugging numbers into a production function, and we're using what we know about the production function to figure out the wage rate and the rental price of land and the factor share of income. Okay, so first off, this question is borrowed from Menkew's Macroeconomics, 8th edition, on the chapter on the open economy, chapter 3, problem 2. So it asks, suppose a production function of medieval Europe takes this form, y equals k to the 1/5 times L to the 1/5, where k is the amount of land and L is the amount of labor. Given that the economy begins with 100 units of land and 100 units of labor, use this information and a calculator and equations to find numerical answers for each of the following questions. So starting off with how much output does this economy produce? So step one in something like this is always just kind of organize the information that you've been given. Step one, organize your information. First off, we have the following production function. This guy right here. And then we're also given information about how much land and how much capital and how much labor there is. So up here we're told that there's 100 units of land. So that's K in this model. So land equals 100. And then we're also told up here that there are 100 units of labor, L. So that's L equals 100. So part A here asks, how much output does this economy produce? So for that, you start with the production function here. To kind of review what we're looking at with this production function, you have Y for output. In macroeconomics, you're going to see Y as referred to as output, as real income, sometimes as GDP, that sort of thing. But what Y is Y is a function of some inputs. So in this case, we got K for land and L for labor. And it takes these inputs, so these factors, and then produces some quantity of output, right? So how does it take those inputs? Given a certain amount of K and a certain amount of L, how much output does it produce? Well, that's defined by this production function here. So this takes the form of a Cobb-Douglas production function, a Cobb-Douglas that actually has some parameterization to it. So just for reference, a Cobb-Douglas looks like this. Generalized Cobb-Douglas will look like this. So it's a generalized Cobb-Douglas production function where you have technology here, that's A. K for capital is raised to this alpha, and then L is raised to 1 minus alpha. So the exponents above the two factors, K and L, is going to equal 1 in a Cobb-Douglas. And then with this production function, you can see we've kind of simplified it a bit. So we've set A, technology, equal to 1, and then alpha here is set to 0.5. So 1 minus alpha is just 1 minus 0.5 or 0.5. So you can see this is kind of like a parameterized Cobb-Douglas production function, where this is in another video, I'll kind of discuss Cobb-Douglas, but for now, let's let Cobb-Douglas sit to the side, and we're just dealing with this production function. So in order to find what output this economy is making, all we have to do now is plug in the numbers. So K is 100, L is 100. So what's 100 to the 1/5? That's the square root of 100, or 10, times the square root of 110. So it's going to equal 100. So our answer here is 100. So the output of this economy is 100 units of production. Okay, so far, so straightforward. For part B, it asks the following. So what is the wage and the rental price of land? So the exact wording of this question is a little confusing, because when we talk about the wage, I'm pretty sure they're talking about the real wage, because the wage that we're given is the following equation. The equation for wage is the following. You have W, which is stands in for a notation for wage, times the price level, or is equal to the price level times the marginal product of labor. And then the real wage is the wage adjusted for prices, which is just equal to the marginal product of labor. So I think this price level, this P in here, sometimes confuses people. You kind of conceptually know what the wage is. The marginal product of labor we'll get to in a second. But then, so what is this P? How do I solve for P? For P, in general, kind of know what it is. So it's the price level, and it's an index. It's a number that represents overall prices. And you could think of it. I guess you could think of it as an index that turns values, so this marginal product of labor, into kind of like prices, costs. So marginal product of labor is the value of an additional unit of labor. And so you take that value, an additional unit of labor, times the price level, and then you get the wage. And the wage is the price, the actual cost that a firm is willing to pay for that extra unit of labor. So you go through this mechanism here to convert the value into prices so that you have a dollar amount you could pay them. Now, real wage kind of gets rid of prices, or I guess corrects for prices. So the real wage rate is the wage, the nominal wage here, controlled for prices, so divided by prices, and that gives you the actual value, the marginal product of labor, the value of an extra unit of labor. So that intuitively and not very well explained is what the price level is. But in this class, in fact, for most of intermediate macro, unless you're dealing with like inflation models, so like money demand model or the Fisher equation, just think of this number here, P, as 1. So try not to let it bother you. You can see by letting it equal to 1, it's just wages is equal to the marginal product of labor. The real wage is equal to the marginal product of labor. So in the back of your mind, if the price level is confusing you here, just kind of set it to equal to 1 and move on. So what is the wage rate? What's the real wage rate? Well, when we talk about wages here, I'm going to solve for the real wage rate, and that's totally fine for this problem. The real wage rate is equal to the marginal product of labor. So what's the marginal product of labor? So the marginal product of labor, this MPL, once more, is the value of an extra unit of labor brought into this firm. There's a couple ways you could solve for the marginal product of labor. One way is you could start off with the production function here. You could put in 100 for capital and 100 for labor, find out what the production is. That's going to be 100. And then the next step is increase labor by 1. So set labor to 101 and find out how much production increases. So that is, so I'm going to call that like the incremental method. You start with this production function, you plug in 100 land and 100 labor, and we got the result of 100. And then you increase labor by 1, so now you have 100 capital and 101 labor. You kind of just churn it out, solve this through, and you now get an output of 100.05. So the difference between the value of adding an extra unit of labor is the difference between 100.5 and 100. So the marginal product of labor is just 0.5. But we're going to have kind of a more general way to solve that. So let's just put this way to the side. Some people like when they start solving this problem, start off by doing this method. But what you want to do is the method I'll get to right now. So the marginal product of labor is the value of an extra unit of labor. And if you remember calculus, you could actually find, by taking the derivative of something, you could find how one thing changes when you change another thing. So we have y, our output, and it's equal to this equation. So what we could do is take the derivative of it. So we're curious, we want to know what how output changes. So die y, the change in y, given a change in labor. So we're going to find how output changes, y, given a change in labor. So that is equal to this. So just taking the first derivative of the production function with respect to labor. So what's the first derivative of the production function with respect to labor? You bring the exponent down, so now it's 0.5 times k raised to the 1/2, just like normal. And then L is raised to 1 minus its old exponent. Which is just negative 0.5. So this guy right here is our marginal product of labor equation. And then just through algebra, we could simplify this quite a bit. So the second line right here is equivalent to the first line. Anything raised to a negative number is equal to 1 over that raised to the positive of that number. So this k divided by L all raised to the 1/2 is equal to this portion right here. So the next step, let's just plug in the numbers that we're given. So for k, we're given 100, and for L, we're given 100. So this just comes down to 1. So 1 over 1 raised to 80 power is just 1. So the marginal product labor is 0.5, which is exactly what we found using this kind of incremental method. So we have marginal product labor equal to 0.5. Next, I want to talk about the marginal product of labor given any production function. You'll notice in practically any intermediate macroeconomics textbook you'll be given the following for the marginal product of labor. So, first off, you have the Cobb-Douglas production function. So A, k raised to the alpha times L raised to the 1 minus alpha. So the marginal product of labor is going to be just the first derivative of this production function with respect to L. So that's 1 minus alpha times A, k So this equation right here, marginal product of labor is equal to 1 minus alpha times technology times k over L raised to the alpha. And then just for good order, I'll have a couple other ways that this could look as well. So these are all equivalent. It's just another way to kind of organize your information. So k to the alpha, L to the negative alpha is equal to this little portion right here. And then also one thing that you might notice is that 1 minus alpha A k to the alpha, oops, All right. So playing with the exponents a little bit, the marginal product of labor is also equal to this little thing right here. So L to the 1 minus alpha divided by L is just equal to L to the negative alpha, right? So you could actually simplify this a little bit more to the following. So I'm going to take away the L, bring it to the outside. So this is all still the marginal product of labor. All I've done is kind of rearrange exponents and added and removed terms to keep it, equal to the same thing. And you have a 1 minus alpha times ak to the alpha L to the 1 minus alpha. Notice that this is just the production function up here. So this is just y. And then all that divided by the quantity of labor. So all of these different things here are equivalent to the marginal product of labor given a Cobb-Douglas production function. And different questions, it might be more useful to use one form or the other. For example, this one right here, 1 minus alpha times y over L. This guy right here is just kind of like labor productivity. It's the output, y, divided by L, the number of workers. So it's like the average output or the output per capita. And then these two over here, I don't know, they're kind of easy to derive and easy to work with. So you might initially start with marginal product of labor that takes this form. All of these are going to give you the exact same answer because they're all equivalent to each other. And then you notice with this production function that we're given, alpha here is 0.5. But this functional form for the marginal product of labor is exactly equivalent to these guys over here. All we've done is plugged in alpha, which is 1/2, and we plugged in our technology, A, which is just 1. So these guys are good to know how to work with because they're a generalized version of a specific production function, like the ones you're given here. But very often you can be asked to use, the Greek letters, alphas, and that sort of thing. Okay, so this is taking way longer than I thought. So I'm going to get through the marginal product of capital, the rental rate of capital, pretty quickly. So the production function was k to the 0.5, L to the 0.5. So if we want to find how output changes, die y, given a change in capital, given a change in land in this case, so die k, we need to take the first derivative of this production function. So the exponent above k is 1/2, so 0.5 times k to the 1 minus 0.5, which I'll simplify in a second. And then L, is unchanged, so it's going to stay the same. So this is our marginal product of capital, or our rental rate of capital. And then you could, the form it takes right here is correct, right? This is the marginal product of capital, but it's useful to simplify it. So I'm going to do 0.5 times because that kind of looks nice. So let's plug in our numbers. We're given actual numbers for labor and capital. Labor was 100, capital was 100, all raised to the 0.5, but 100 over 100 is just 1. So this whole thing is going to go away, and you're left with the marginal product of capital, which is equal to the rental rate of capital of 1/2 again. So the wage rate's 1/2, and the rental rate of capital is 1/2. Cool. So I'll link to the rest of the questions in the video description if you want to have a look. Hopefully this was helpful. Thanks and have a good day.